students, let's begin today's session. So we have almost completed radiation last time, where we saw the application of Stephen Boltzmann's law of radiation. Along with that, the Newton's law of cooling, experimental law, and how Stephen Boltzmann law can reduce to Newton's law of cooling under the condition that the temperature of the surface of the body, the difference of that temperature with respect to the surrounding temperature is comparatively small. So how the condition that we get from Stephen's law reduces to Newton's law of cooling. So a couple of types of numerical problems we'll look at related to this first, and then the final part of radiation, which will be about spectral emissive power and Wien's displacement law and something called the ultraviolet catastrophe. We'll discuss about that, and with that we'll wind up this section of heat and thermodynamics today. So let's begin. So what we had seen as part of radiation, Stephen's law, that if we have a body which has a surface at a temperature of T and surface area S, and the surrounding temperature is T0, then the net rate of heat loss, of course, assuming that the temperature of the surface is greater than the temperature of the surrounding. So that is proportional to T to the power 4 minus T0 to the power 4, where the proportionality depends on all these things: the emissivity, the universal Stephen's constant, the surface area, etc. Then we had seen that if T is equal to T0 plus delta T, such that delta T by T0 is extremely small compared to 1, then this term T to the power 4 minus T0 to the power 4, by binomial approximation, it becomes 4 T0 cube delta T, or 4 T0 cube T minus T0. So in that case, further we can say that the net rate of cooling or net rate of heat loss becomes proportional to T minus T0, for delta T by T0 being very small compared to 1. And therefore, from that we can say that the rate at which the temperature is dropping, or what we call the net rate of cooling, is proportional to T minus T0. So this was actually the statement of Newton's law of cooling. Okay. But the constant of proportionality here actually comes by analysis of the Stephen's law of radiation. So let's begin with a question based on that, how to develop that relation for the constant of proportionality. So we have a solid metallic sphere. So it has all these properties. Radius is 10 centimeter. The emissivity of the metal is, let's say, 0.25. Okay. The density of the metal is, let's say, 12 gram per cc. And the specific heat capacity of the metal is 0.2 joules per gram degrees C. And let's take the universal Stephen's constant as 5.7 into 10 raised per minus 8 watts per meter square Kelvin to the power 4. So now the question is that if the metal or the metallic sphere's surface is at a temperature of, let's say, 32 degrees C, and the surrounding atmospheric temperature is 27 degrees C, then find the rate of cooling in kelvins per second. So this will be a numerical application of what we are just talking about above. Just try this out, we'll discuss. Yeah, so anybody work this out? So let's understand what are the geometrical factors you will take into account for a spherical body, solid spherical. So the surface area will be 4 pi r square. Okay. The volume will be 4 by 3 pi r cube. So the mass will be density into volume. So So the heat capacity will be mass into specific heat capacity. So these are some of the things that you'll have to take into account. So the net rate of heat loss will be E sigma into surface area. Now in this, T is 32 degrees C or 305 Kelvin, and surrounding temperature is 300 Kelvin. So you can see that delta T is 5 Kelvin, which means that delta T by T naught is very small compared to 1. So T to the power 4 minus T naught to the power 4 will approximate as 4 T naught cube delta T. So next step, replace this with 4 pi r square, okay, into 4 T naught cube into delta T. And further, this becomes so next step, the rate of cooling divided by density into volume into specific heat capacity. So 4 pi r square we can cancel out. So the 3 goes on top. So we have 12 E sigma T naught cube upon density into R into specific heat capacity. This into the temperature difference. Now we can substitute the values in SI unit. So we get the rate of cooling initially. Aman, I think there might be some order of magnitude issue with your answer. Just check that you substituted all the quantities in SI units. Anybody else got the answer? All right, you want to see the values now. So here are the values. I'll just put them below here. also so these values I've already given you here, and rest of the things are here. Just a minute. The density was 12 gram per cc, so I just okay. So nothing but substitution now. You have to just make sure you substitute everything with the proper unit. So for example, this will be 0.1 meters. This will be 12 into 10 raised power 3 kg per meter cube. Okay. This will become 0.2 into 10 raised power 3 joules per kg degrees or joules per kg Kelvin. Okay. And this is fine. This is an SI unit. Okay. So the rate of cooling this will become into the temperature difference, which is 5 Kelvin. So in Kelvin per second, it will be very small actually, the rate of cooling. Sorry, this should be 27 and not 9. So I'm getting something like this. 9.62 approximately. Into 10 raised power minus 5. Kelvin per second. So if I just multiply this by 60, and get it in kelvins per minute. So extremely slow rate of cooling, as you can see. And these are typical values in terms of order of magnitude. So something like 0.006 kelvins per minute. Okay, so hope this is clear. Now let's look at another type of problem related to Newton's law of cooling. So now we have a metallic body is initially at a temperature of 31 degrees C at time t equal to 0 and is cooling at the rate of per minute. Okay. The surrounding temperature is equal to 27 degrees C. So first of all, find its rate of cooling when its temperature has dropped to 28 degrees C. And secondly, find the time taken for its temperature to drop from the initial value of 31 degrees C to 29 degrees C. And again, find the time taken for its temperature to drop from 29 degrees C to 28 degrees C. Okay. So this is another type of question where you have to use that integrated form of Newton's law of cooling that we were talking about last time. Remember that exponentially decaying graph, that kind of relationship you have to use over here. Just try this question out, people. Density is Nikita 12 gram per cc in that one. So it was 12 into 10 raised by 3 kg per meter cube. I hope I've substituted that correctly. Yeah. This density, na? So this is the SI unit. Hope this is clear. Oh, achha, you had written 22 by mistake. Okay. Okay, let's come to this question. Okay, so while solving a question like this, now we have to understand that yes, Naman, that's correct. Kevin, your answer is also correct. Okay, so we have to understand that which change in temperature, or rather which rate of change we can approximate as an instantaneous rate of change, and which is the average rate of change. Okay, because as you know, we have these two equations. Okay, in the differential form, we have the rate of cooling is equal to some particular constant into temperature difference. Okay, so let's say, so this is not heat capacity, this is just this constant of proportionality. Okay. But when we integrate this at T equal to 0, if the temperature of the surface is the initial temperature and T equal to T, the temperature is an instantaneous temperature T, then on integrating this, we get this relation that it is T naught plus the initial temperature difference into that exponential factor. And the coefficient of time in that exponential factor is this very constant c. Okay. So now the thing is, like, when do we use this second equation and when do we use this first equation? So you can see that for small change, we can do this. We can use this relation. Okay. But for significant change, we cannot say the instantaneous rate is equal to the average rate. So this is the key, when you have to use this and when you have to use this. Okay. Now you see that the temperature of the surface initially was 304 Kelvin in this case, and the temperature of the surrounding is 300 Kelvin. So this initial temperature difference is 4 Kelvin. So therefore, the first statement that is given, that in 1 minute, the temperature drops by 0.02 Kelvin. Okay. So this can be treated as a small delta T, because the temperature difference with respect to the surrounding is 4 Kelvin. So overall, the temperature has to drop by 4 Kelvin. So compared to that 4 Kelvin, that 0.02 Kelvin is small. So we can say that the instantaneous rate at that moment is approximately equal to the average rate, which is 0.02 by 60 Kelvin per second. Okay. So again, if you think graphically, okay, when we are talking about this change of 0.02 Kelvin, we are talking about 2 points which are so close that the line joining them, you can think of them like the tangent line instead of the secant line. So you can get away by using the instantaneous rate formula. That is equation number 1. Whereas when we are talking about the temperature dropping from 31 degrees C to 29 degrees C, that's a 2-degree change. So that is significant compared to this overall temperature drop that's going to happen. So we cannot treat that as a small change. We have to, so this initial value of temperature and this surrounding temperature 300 Kelvin. So we look at the overall temperature drop. It's like this. So when we are talking about a temperature dropping to 302 Kelvin, and we're talking about a significant change between this point and this point. But when we're talking about a temperature drop of just 0.2 Kelvin or 0.02 Kelvin, okay, so then that's very close. The temperature here is initial temperature minus 0.02 Kelvin. So for that, we can treat it like the tangent line. Okay, this one. But for a delta T equal to minus 2 Kelvin, okay, from 304 Kelvin to 302 Kelvin, this is not a small change, because the overall range of temperature dropping only is 4 Kelvin. No? So when it's dropping by 2 Kelvin, it's half of it. So hope this point is clear to you all of you. Okay. So now coming back to this, from this data, we can actually find out the value of C. So therefore, so if we apply this at the instant T equal to 0, when T is the initial temperature equal to 304 Kelvin, and the rate of at which the temperature is dropping is 0.02 Kelvin per minute. So we can see that 0.02 Kelvin per minute is equal to this constant into 304 minus 300. So that means this constant of proportionality only is 0.005 minute inverse. That is the value of this constant. So this is one useful information that we're getting. Okay. So now from this we can also see that when the temperature of the surface becomes 28 degrees C, or that is 301 Kelvin, at that point of time the rate of cooling will be the same constant, but now into this temperature difference. This is 1. Okay. So this will become 0.005 Kelvin per minute. So that will be the rate of cooling at the instant when the surface temperature is 301 Kelvin. Okay. Or we can just understand this by ratio and proportionality. The temperature difference initially was 4 Kelvin. And at this instant, the temperature difference, okay, so you can see that T initial minus T naught was 4 Kelvin. And at this instant, T minus T naught is 1 Kelvin. So delta T is 1/4. So the rate also has to become 1/4. Okay, so that is 1/4 of 0.02. That's an even simpler way of understanding this part. Okay. But now when it comes to the second part, where we are calculating the time taken for the temperature to drop, not the rate, or not by 0.002 or 0.0005 or something. We're talking about the time taken for it to drop all the way from 304 kelvins to 302 kelvins. So by a significant amount of 2 full kelvins, then we have to use the second integrated equation. Okay, temperature as a function of time has to be used. We cannot use the instantaneous rate of change. Aman, your answer seems to be correct. Okay, I'll just verify once. Naman, you have to check the order of magnitude of your answer. Might have made some mistake with some multiplication or some power of 10 or something you missed out. Yeah, Naman, your answer seems to be correct now. What about the answer to the third part from 29 to 28 minutes, 29 to 28 degrees C? Okay. Now, of course, I'm assuming that you people have done a bit of approximation in the calculation because the answer will come in terms of log ln, okay, and you will have to convert. Okay. So anyhow, let's see. So when I substitute this equation over here, that temperature as a function of time is this thing. The equation that I get in this case is that temperature is equal to 300 plus 4 e raised power minus Ct, where I know the value of C is how much? What was it? The value of C that we had got. Yeah, 0.005 minute inverse. So that value of C will use. Okay. So now you can see that at T equal to 0, the temperature is equal to 304. That's okay. But at some time, let's say T1, the temperature is equal to 302 Kelvin, or that's 29 degrees C. So you want to find this time T1. So substitute this in equation 1. So 302 should be equal to 300 plus 4 e raised power minus Ct1. So this equation will give us the value of T1. So as you can see that 2 is equal to 4 e raised power minus Ct1, or e raised power minus Ct1 is equal to half, which means that e raised power Ct1 is equal to 2, which means that this is natural log of 2. So T1 should come out to be ln2 divided by C. So that is approximately 0.7 divided by 0.005. And now this answer will be in minutes. So I'm assuming Aman and Naman, both of you have done this calculation. So this is 7 by 5 into 10 raised power 2 हो जाएगा ना minutes. So you should be getting this as 140 minutes. Okay. So this is the time T1. Now, once again, you apply the same thing, but for a different time T2, when the temperature has dropped to 301 Kelvin, which is 28 degrees C. So you get okay. So when you do this calculation, you'll see that you'll get e raised power minus Ct2 as 1 by 4, which means you will get T2 as ln 4 by C, which you can write as 2 times ln 2 by C, which you will see is 280 minutes. Okay. So this is going to show us something interesting, that the time interval taken to go from 31 to 29 will be the same as the time interval to go from 29 to 28, which is 140 minutes. So this shows us a very interesting property of the exponential graph, the exponential decay graph. If you have seen the exponential decay graph of radioactive decay earlier, you will recall that there's something called half-life. Okay. And an important concept of half-life, that every half-life, the number of radioactive nuclei becomes half the initial value. So a similar property of the exponentially decaying curve is actually in place over here, which is why it's no coincidence that we are getting the two intervals of time as the same. 31 to 29, whatever time it's taken, 29 to 28, it's taking the same time. So it's not exactly a coincidence. That's happening because of that nature of the exponential graph. I'll explain in a moment. Just note down up to here first. Okay, so let's come to that property of that exponential graph, which I tell you. Property of exponential decay. Okay, if we have a graph of y is equal to e raised power minus x divided by some value, let's say capital N, okay, where n is just a constant, like example n might be 50 or something like this. Then when we look at the exponentially decaying graph, the value of y if we just look at the non-negative domain of x, x greater than equal to 0, then as you know, the value of y drops like this. And very slowly it approaches 0. So it starts from the value 1. Now it becomes the value exactly half in a certain value of x, let's say, let's call that x half. Okay. Then it becomes 1/2 of that. That means it becomes 1/4. Now that value is exactly double of this value. Okay. And then it becomes 1/8, and so on and so forth, at a value of x equal to 3 times x half and like this. Okay. So from this we can see that y is equal to 1 at x equal to 0. Y is equal to 1/2 at x equal to x half. This will give us the relation that x half is equal to this constant times ln2. Okay. So y will become 1/2 to the power n at x equal to n times x half. That is n times n ln2. That is the idea over here. This is the property of the exponential decay. So I'll relate it with this also. So for example, if we had a graph like this, where we have some parameter like y, which is some constant, let's say, into e raised power minus some constant into time. So you can see that beta is a constant which has dimension of time inverse. Okay. So again, when you look at the graph of y versus time in this case, this exponentially decaying graph, it would have the same property. That if y started with a value alpha initially, then its value would drop to half of alpha at a time which we can call as a half-life. Then it would drop to 1/4 of alpha at a time which would become 2 times this half-life. And like that, it would drop to alpha by 2 to the power n at a time which was equal to n times half-life. Okay. And this half-life would be equal to ln2 by beta, which you can see from this. Okay. You can see that alpha by 2 is equal to alpha e raised power minus beta into t half. So t half is ln2 by beta. So this is an important property of the exponential decay graph, which you should know, because it's going to be significant for us not only in this chapter, but in future chapters also. For example, even in kinematics, if you're dealing with a situation where there is a retarding force or a this thing, what is it called? A drag force, which is proportional to the speed and opposite in direction, then you get this kind of exponential decay for speed versus time. You know, I'll explain how that's working over here also in this particular question. But resume it. Yeah, okay. Right, so I'm resuming the recording. So let's continue with the explanation of this question. So what I was explaining is the nature of the exponential graph like this. So in this case, we are looking at the graph of this thing, that temperature is this factor, which over here is becoming that temperature is 300 plus 4 into e raised power minus ct. Okay. So it's like the exponential graph we were discussing previously, but it is slightly transformed. It's not decaying from some value to 0, but it's decaying from 304 to 300. Okay, so the temperature is decaying with time from this value, initial value 304, to this final value, let's say 300. Actually, I've drawn it this way, but you can see that this difference is actually a very small difference. So this graph is not exactly drawn to scale. Okay, so now when we look at the temperature versus time relation, because it's that exponential kind of graph, so you can see that when it reaches this midpoint, the temperature is, let's say T1 302, and then the further midpoint of this and this, or the 1/4 point of this, when the temperature becomes 301. So if this time is, we label it as T half, because the temperature difference, this delta T was equal to 4 Kelvin at T equal to 0. So now the delta T has become equal to 2 Kelvin at T equal to T half. Okay. So further the delta T will become 1 Kelvin at T equal to 2 times this half-life. The delta T will become 0.5 Kelvin at T equal to 3 times. And where the formula for the half-life is ln2 divided by C, which was coming out to be 140 minutes or 2 hours and 20 minutes. Okay. So that's why this was happening. So this was 140. So this next time interval, this will also be a value of 140 minutes. My graph is not according to scale, but still this will also be 140 minutes. Okay. So that's why the time is 280 minutes. And similarly, it will become 300.5 in the next 140 minutes. Okay, then it will become 300.25, and like that the geometrical progression will go for the temperature difference. This temperature difference will go from 4 to 4 by 2 to 4 by 4 to 4 by 8, and like that. In half-life, 2 times half-life, 3 times half-life, and so on and so forth. So that's an interesting property, you can say, of the exponentially decaying graph, which we'll see again and again in physics, not only in this section, but other parts of physics also. For example, when we look at decaying current in a capacitive circuit in future, when we study about capacitors as part of electrostatics, or very soon we are going to come to the chapter of viscosity. So there we will see Stokes' law and the concept of terminal velocity. So there also there'll be a similar type of concept coming in. Exponential graphs. Okay, so this brings us to the conclusion of this section, applications of Newton's law of cooling. Now we come to the last part of radiation, which is to do with the spectral distribution of electromagnetic radiation. Okay. So as we know, radiation is heat transfer through electromagnetic waves. Okay. Both absorption or emission. So when we look at black body radiation, in particular, or any type of body actually. But particularly when we look at black body radiation and we want to study the spectral distribution of electromagnetic radiations. So by spectral distribution, we mean distribution of the electromagnetic radiations over the electromagnetic spectrum, that is the range of wavelengths or frequencies of electromagnetic waves. So that particular aspect of radiation is called the spectral distribution. So as you know, the electromagnetic spectrum is an extremely diverse spectrum of EM waves. Okay. The lowest wavelength is for gamma radiation, which has maximum frequency and minimum wavelength. And at the other end of the spectrum, we have radio waves, which have maximum wavelength and lowest or minimum frequency. And of course, electromagnetic spectrum is such that C is equal to F lambda, where C is speed of light or EM waves in vacuum or air. Okay. So somewhere in between comes the visible light, for example. Visible light comes in a range of, you might have heard, 400 nanometer wavelength to about 700 nanometer wavelength. Then we have, for example, we have X-rays. They have wavelength of the order of angstroms. Okay. We have microwaves, which, as the name suggests, the wavelength is of the order of micrometers, order of magnitude of micrometers. Okay. We also have infrared, ultraviolet, etc. Okay, so how the energy radiated, particularly by a black body, is distributed in this spectrum, that aspect is called the spectral distribution of radiation or electromagnetic radiation. And that is studied by studying the particular property which is called spectral emissive power. Okay, just like we have studied a physical parameter of emissive power, like that we will study spectral emissive power. So it is like a specific emissive power at a particular wavelength. That is the meaning of the term spectral emissive power. Okay, so let's look at the parameter called spectral emissive power. It is denoted by a symbol like this. So it is basically the emissive power specific to a certain wavelength, lambda. Okay. So spectral emissive power is the energy emitted per unit time per unit surface area at a specific wavelength, lambda. Whereas emissive power is simply the total energy for all wavelengths emitted, that is over the entire electromagnetic spectrum. Okay, so the total energy emitted per unit time per unit area. Okay. So as you know, spectral emissive power Yeah, Vineet, I'll go back to the flow chart. Okay, so so emissive power we know is sigma into T to the power 4 for a black body. Or for a normal body, it is emissivity into sigma into T to the power 4. But this is spectral emissive power. You can also say that it is the fraction of E which is being emitted at a particular wavelength, lambda. Whereas this is total energy radiated over the entire electromagnetic spectrum. So you need not note down this electromagnetic spectrum. I've just given very basic information in this. You will find much more detailed information about the electromagnetic spectrum in your optics chapters, wave optics or electromagnetic waves chapters in H.C. Verma part 2 or any reference book like that. Or on the net also, if you just look at EM spectrum, you'll get a much more detailed analysis about it. But the whole point is that when we are looking at a material or a body emitting heat or emitting radiation, that emission happens over an entire spectrum. So now we want to look at how that energy radiation happens with respect to the different wavelengths. Yeah, sorry, my connection had gone off for a minute. Yeah, so let's look at the definition of spectral emissive power again. So it is the emissive power at a specific wavelength or at a particular wavelength lambda. So if emissive power is the total energy per unit time per unit area emitted over the entire electromagnetic spectrum, then a certain fraction of that energy or a certain part of that energy is at a particular wavelength in the spectrum, lambda. So that fraction of the total energy per unit time per unit area at that particular wavelength lambda is called the spectral emissive power for lambda. So spectral emissive power has different values for different wavelengths at a given temperature. So now the relationship between spectral emissive power and wavelength at any given temperature, that looks like this. If we draw the graph of the distribution of energy over different wavelengths in the EM spectrum, that will give us the pattern of the spectral emissive power, okay, or the pattern of the distribution over the spectrum. So that typically looks something like this. That graph peaks at a certain value, and then of course it starts from zero, of course. So it's logical that there is zero energy at zero wavelength, but it sort of peaks and then tends to go towards zero as you go to the higher values of wavelength. So at a particular wavelength, which is called the peak wavelength, we get the maximum energy. That means the maximum fraction of the total energy is around that wavelength. And this is for a specific temperature T. So this graph, we have to just treat it like a experimentally determined graph. For black body radiation. Of course, a perfect black body does not exist. So it's observed for materials which are very close to perfect black bodies, which have very high value of emissivity. Okay, so hope this part is clear. Now let's understand the interpretation of spectral emissive power. So when we look at a particular spectral emissive power graph at a particular temperature, say it's like this. Now, one important thing to understand about this graph is, if we are looking at a particular wavelength, let's say lambda, okay, and at that particular wavelength, we are getting a certain amount of energy per unit time per unit area. So we're getting that value E lambda. Now, if we take a very close value to it, such that this interval is D lambda, and we draw a vertical strip like this, and we calculate the area of this strip. Okay. So the area of that strip will be a differential area. It will be actually E lambda into D lambda. Okay. So it will be equal to, it will be the energy per unit time per unit area. Okay. That is, this is not the area of the graph. Okay, this is per unit surface area of a black body. Okay, emitted in the range of wavelengths lambda to lambda plus D lambda. In that very short range of wavelengths, the amount of energy per unit time per unit area, that's that. Okay. So now if we integrate these strips and find this total area, so therefore total area under the E lambda versus lambda graph, that becomes this. Okay, and that becomes nothing but the total emissive power. That's one important aspect about this graph, that the area under the graph is equal to, in the total area, that is equal to E into T to the power 4. And the other important thing about the graph is the relationship between the peak temperature, the peak wavelength, and the temperature at which this graph is existing. So if the temperature of this black body is capital T, then the other observation we have, that the value of this lambda peak is inversely proportional to the temperature, or absolute temperature into the peak wavelength is a universal constant called Wien's constant. Okay. And related to this, we have the statement of Wien's displacement law, which I'm coming to next. So Wien's constant's value is nearly 3, or 2.898 into 10 raised power minus 3 meter Kelvin. Again, you don't have to remember the value, just know its significance. So the significance of this is this, that the peak value of wavelength is inversely proportional to the temperature. So when we increase the temperature of the body, the peak value of wavelength decreases, whereas the total emissive power, of course, increases because it's proportional to T to the power 4. So that is something significant and important to understand.
Sir, why is the maximum lambda inversely proportional to temperature?
Yeah, so that's a very good question why it is the case. And the answer to that, unfortunately, is very complicated. And this was, as I told you, there's an experimental law initially, but the explanation for this resulted in a principle called the ultraviolet catastrophe. This results from the fact that the lambda of the peak value is inversely proportional to temperature. Now, about this, there is no explanation in classical physics, or in fact, there is a contradiction. Okay. There is a contradiction in the classical physics model. So the classical physics model, for example, included the concept of the normal principles of thermodynamics. Along with that, the statistical mechanics concepts. So statistical mechanics is a sort of extension of the Newtonian mechanics kind of principles that you have studied, which is then applied to a many particle system, like an ideal gas or a real gas or something like that. So it's closely related to thermodynamics. So that kind of classical physics failed to explain this. In fact, it contradicted this. So the explanation emerged from quantum mechanical principles. Okay. And this was one of the early successes of quantum mechanics. So that's why in the history of physics, particularly in the history of quantum mechanics, it's a significant achievement. Okay, so it's one of the early successful, you can say, successful applications of quantum mechanics. And it resulted in the acceptance of quantum mechanics to a large extent. Just like, you would have studied in chemistry that the line spectrum of hydrogen-like atoms, the Lyman series, Balmer series, that line spectrum, it could not be explained by classical physics for a long time. But then came in the quantum mechanical explanation that there is angular momentum quantization that happens for electrons in orbital motion. And that explained why the spectrum of radiations from hydrogen line like atoms should be line spectrum and not continuous spectrum. So this was something similar. Okay, so unfortunately, because of strong background that is required in mathematics for studying quantum mechanics, we can't get into it at the 10+2 level. In fact, quantum mechanics is something which people properly get into only at the graduate level in physics. But as your general knowledge goes, you should understand this, that this Wien's displacement law and the ultraviolet catastrophe as a result of that the peak wavelength is inversely proportional to absolute temperature. The only successful explanation of this comes from quantum mechanics, and it is actually contradicted by classical physics. So that is why this was one of the early successes of the quantum mechanical model in physics. So that's why it's a significant event in physics history. Okay, so that's all we can at this stage understand about it. Okay. Yeah, Amog, I'll scroll up for a second. So hope that answers your question, Vita, to a certain extent, right?
Yes, sir.
Okay. Now, the other aspect about this spectral emissive power graph that we should know is how we can compare the spectral emissive power graphs at two different temperatures. So basically, how a black body's emission with respect to the spectrum, how it behaves as its temperature is changed. Once if we measure the distribution over the spectrum at a lower temperature, and then later we increase the temperature and we compare the two, how it will change. Let's understand that. So spectral emissive power versus wavelength. Now suppose I'm doing the experimental analysis and I've come up with this kind of a graph. This won't be a straight line, of course. It will be more like kind of a curve. So I'm getting a peak value of lambda 1 at some temperature T1. And what will happen also is that the area under this graph, area at temperature T1, that will be proportional to T1 to the power 4. Okay. Now, if I increase the temperature, I'll see that the graph actually shifts like this. It shifts in such a way that it cannot cross this graph anywhere. But the shape of the graph changes such that the peak value changes. And also the shape of the graph changes such that the total area changes now. So the new area at T2 will be proportional to T2 to the power 4. Okay, so the ratio of the areas is the ratio of the temperature to the power 4, but at the same time, lambda 2 by lambda 1 will be equal to T1 by T2. This is from Wien's displacement law. So why it's called a displacement law is to understand how the peak value of spectral emissive power, the peak value of the wavelength shifts according to a change in temperature. Whereas this earlier statement that you can see, this is from Stephen's law of radiation. So the total area under the graph will have to increase in such a way that it's increasing by a factor of T2 by T1 to the power 4. But the peak wavelength will decrease in such a way that it's going to T1 by T2. So here obviously T2 is greater than T1. So as the temperature increases, the peak wavelength drops or decreases, whereas the total area, which is the emissive power, decreases. So since this is just a sort of formula based kind of situation for us in physics, because we cannot get into the derivation of this because it comes from quantum mechanics. So it's not really significant from JEE Advanced point of view. In JEE Mains also, you can at the most expect one formula based question based on Wien's displacement law. But the major part about heat transfer will be from conduction and radiation. And in radiation, the two things that we've discussed, the application of Stephen's law directly and the application of Stephen's law in the special case where we can do the approximation and reduce it to Newton's law of cooling, and then that integrated form of Newton's law of cooling, the temperature versus time graph. These are the things from which the significant numerical problems and all will come in JEE. Okay, so with that we conclude this section, heat and thermodynamics. Now next week onwards we will be starting with a new section of physics, fluid mechanics, moving on to properties of matter after that. So immediately the chapter we'll be doing afterwards, after this, is going to be hydrostatics and then hydrodynamics, which is part of fluid mechanics, right? So hydrostatics will deal with things like Archimedes principle and floating objects and concept of buoyancy, etc. Whereas hydrodynamics, the next part, will deal with Bernoulli's equation and streamline flow and continuity equation and things like that, velocity of efflux, flow of a liquid in streamline motion. And from there, we will move on to properties of matter, where we'll first look at elasticity and then eventually surface tension and viscosity. So that's what's coming up for us in the next week. Okay. In between, of course, you will be having another test coming up on 16th expectedly. You will get the announcement for that soon. And for that, you can expect the entire heat and thermodynamics syllabus along with also rotational mechanics. Okay. So again, at this stage, the more important part of your syllabus is is the mechanics part, because that has more weightage. Whereas at the same time, heat and thermodynamics is easy. So if you just do all the questions, you can expect to score with more accuracy compared to mechanics. So from scoring point of view, these topics are also very important. Okay. Whereas in terms of your learning, mechanics will take longer. Okay. Anyhow, so that's it for today's session. People, wish you all the best and thanks for attending.
Thank you, sir. Bye, sir.
Okay,
Thank you.
bye.
Thank
Thank you, sir. Bye.
Thank you, sir.